All right, so I will go through the quiz here. So problem 5. This is quiz 10, right? So I asked you to find the principal third root of 125 e to the 3 pi I over 4. So, and I called this thing z, right? So the way we do that is we take the third root of the modulus of z, the length of z, and then we do e to the I theta over 3. That's the definition of the principal third root. Now here, the modulus of z, the length of it is 125. The standard angle is 3 pi over 4, right? So theta over 3 is what? Just pi over 4, right? And the cube root of 125 is, no. So, oh, well, then I'll know where that number came from on your paper then. That's understandable. You took the square root. Okay, well, thank you for saying that. That will make grading it much more understandable for me. And I don't think you're going to lose a lot on the basis of that, by the way. Okay, so don't fret. So e to the I pi over 4 is what we have there. And of course, that's 5, right? So this is 5 times, and this is what? This is cosine of pi over 4 plus I times the sine of pi over 4. So that is 5, 1 over root 2, plus I times 1 over root 2. And so 5 over root 2 plus I times 5 over root 2. There you go. That is the Cartesian form of the third root of z. That's it. Now, on the graph that I gave you, there's a circle, and that circle has radius 5. And so the first one's at pi over 4, which is right here. And then z to the 1/3, what this is a set of values. The first one is the principal third root. The second one is the third root of unity times the principal third root. And the third one is the principal third root of unity squared times the third root of z. Now here, this funny looking zeta 3 thing is exponential of 2 pi I over 3 by definition. And what that is just a rotation by 120 degrees. So when you're visualizing it, we just have to rotate by 120 degrees each time to find the next answer in the third root. So like this one is at 45 degrees, right? So then 120 degrees more takes me over here to like 165. So there's your, this one, yeah, 285 exactly. Down here somewhere, 285. So I decided asking you to graph the other two third roots of unity would be an easier thing for you to do and for me to see. And if you understand that, that's how the roots of unity, or rather the roots of a complex number are related. They all have the same length, and they're just different, directions. That's an insight I'd be happy if you gain from this course. If you don't, it's like not the end of the world or anything, but that's problem 5. Yo. Problem 4. I said find the polar form of the complex number z equals to 2 plus 2i squared 3, right? So polar form. So I need to find out the modulus of z, the length of z, which is what? The square root of 2 squared plus 2 root 3 squared, which is what? That's the square root of 4 plus 3 times 4, which is 12, square root of 16. So the length of z is 4. You guys get that? No? Ah. But you got it? Oh, you moved already. Oh, thanks. Obviously, I could never be a mom. I don't have eyes in the back of my head. Let's see here. So the angle for z, we can just use inverse tangent, right? Because this z is where, if I'm asked about angles, I always think about myself, a question, where is z roughly speaking? It's like up here, right? So it's in quadrant 1. Now I would say it would be 45, but I have a different x and y component, right? So it can't be 45, it's something else. But so I have the y over the x, so 2 root 3 over 2, which is, of course, just the inverse tangent of root 3. Now we have calculators, so we can just calculate it, but I'll be lazy and show you that this can also be calculated without a calculator. See, because it's actually the inverse tangent of, let's see here, to get sine, I get, tangent of 60 degrees. Anyway, what we're interested in here is pi over 3 radians. Okay, so answer z is 4 e to the pi I over 3. There you go. This is the complex number in polar form. And again, all that monkey business with tangent, special angle, you can just plug in your calculator, get 60 degrees or pi over 3, just the same, right? Problem 3. Maybe I can fit it down here. Let's see here. Problem 3, we have the magnitude of z is 3. The angle of z is 240 degrees, right? So we need to convert that to radians to use the imaginary exponential, right? Or, I mean, so let me show you something. You can either convert to radians, use the imaginary exponential, or you could just, here's another thing you could do. Well, let me show you why. I mean, I will convert to radians, but since it's an important question how you do that anyway. So multiply by pi over 180, you get 4 pi over 3, right? So z is 3 times e to the 4 pi I over 3, right? And I'm asked here to find the Cartesian form of the complex number, right? That's the polar form. So I do 3 and cosine 4 pi over 3 plus I times the sine of 4 pi over 3, right? And, you know, I feel a little bit silly having done the conversion, you see, because I could just as well have kept it in degrees. If, you know, but the thing I'm trying to warn against is we really shouldn't write I times 240 degrees. This is not good to do that. No one does that. But it is true that this is 3 times the cosine of 240 degrees plus I times the sine of 240 degrees. So maybe that's a formula worth having, right? Z is the modulus of z times what? Times the cosine of theta plus I times the sine of theta. You can use theta in degrees for that because everyone understands that cosine and sine can either be interpreted in terms of radians or degrees. Technically speaking, you really should put like a sub-radians or a sub-degrees on the sine and cosine functions because they are two separate functions, as is reflected by the fact that if you don't change your calculator from degree mode to radian mode and you try to use it in the other, it's going to give you the wrong answer. Exactly. But anyway, what is this? This is, so this is minus a half, and this is minus root 3 over 2. So we get minus 3 halves minus 3 times root 3 over 2I. That is the answer to problem 3. I will scan and post the solution after class in case you want to see it again. And I may yet finish creating the website for this course. We're at the end, but for archival purposes, I should make a website for this course I can refer back to, Where was I? Oh, problem 2. This whole working backwards thing, it's an adjustment. Problem 2, oh, you got it? Thanks. Where was I? Find the standard angle in degrees and magnitude of the vector A. We got minus root 3 minus 1, right? So the magnitude of A is the square root of square root of 3 squared, right? Plus 1 squared. You can put minus in there if you want, but the square is just going to eat the minus anyway, right? So that's the square root of 3 plus 1, which is the square root of 4, of course, which is 2. So the magnitude of the vector is 2. And, keep in mind where we're looking here. This is something like this, right? So this is in quadrant 3, which means we don't just use inverse tangent for the angle, right? So calculate inverse tangent. It's helpful. What is the inverse tangent of minus 1 over minus root 3? Well, we just did tangent of root 3. It was 60. I think this is 30. Yeah. So this angle right here is 30 is what that means, right? So you got to add 180 to that. Right, so the angle of vector A is 210 degrees. (180 plus 30). And then finally back to the beginning. We've got this triangle. Angle beta up here, angle alpha over here, 85 degrees right in here. This length is 12. That length is A. This length is 9. And I asked you to find the angle of beta, find beta in degrees, right? So what should you do? And I told you it was an oblique triangle to try to, that's a warning. This is not a right triangle, so don't try to do right triangle trigonometry on it, Law of sines, okay, and so law of sines says what? It says sine of beta over 9 equals to sine of 85, right? Over 12, yeah. And you don't need to mess with the alpha and the A, right? And so that gives us that sine of beta is 9 over 12 times the sine of 85, which gives us that beta is the inverse sine of 9/12 sine of 85 degrees. Now, I know at this point in the course we've been messing more with law of cosines and law of sines, but I would remind you on the final, there will also be problems like we saw on test 1 or test 2 where it was just a right triangle and like find the missing side or angle, right? So remember there, you don't have to use law of cosines or law of sines. You can fall back on just plain old right triangle trigonometry. Don't make the easy problems on the final complicated. Just a, that's just the thought I had. So we got, oh, I already worked it out, didn't I? So that works out to 48.34 degrees. So, you know, I tried to be disciplined on this quiz to only give you problems that were potential final exam problems. And that's the case for all of these, right? Like I was telling Seth, again, but emphasize, no cross products on the final, no three-dimensional vectors on the final. But anyway, it is good that you studied them anyway because, you know, we do live in a three-dimensional world. These are good things to know. So at least three-dimensional world. So I guess that's that for quiz 10. You guys have any questions about the final? I think the other thing that comes to mind right offhand, so I'll just take a couple minutes to talk about the final, and then I'll give you guys the course survey to do. Who wants to take it to the, do you guys know where the secretary is? It's like 118 or something. I'm talking about the secretary for the dean, like the, you know. Do you want to take it? Thanks. No, not, I will hand it out and then leave. So I have it here. No. The in-class course evaluation. This you get 25 points for doing.
On what?
On the course. I made up my own course evaluation. It has exciting questions like, instructor motivated me to do my best work. You can strongly agree, disagree, strongly disagree, or not applicable. Actually, I should do this again, but just put strongly agree in every option. If I made this, why did I make it easier on myself? Not strongly disagree, not applicable. Assignments were evaluated in a timely fashion. Instructor provided helpful feedback on assignments. I would recommend this instructor to a friend. I would recommend this course to a friend. When I recommend a course to a friend, I used to teach almost entirely engineers. So I always had to qualify that with, I'm talking about the friends you have in your same major. I'm not talking about, would you recommend this engineering course to your friend who's in like, we had one major that was essentially how to be a camp counselor or something. It's like, no, the camp counselor people, they do not need to take calculus too, you know? But anyway, I have a 10 multiple choice, choose your own adventure. And then I have like about 5 short answer questions if you have anything to say. Now, the reason I do this is partly because like the electronic one, at least invariably doesn't have enough space to write. And it's just nice to be able to write. You don't put your name on it. And it's fine. I won't not see these until next semester. That's the instructions I'm giving to the secretary. You hold on to them, and then it just helped me because I have to go up for tenure at some point here, and it's helpful for me if I can have evidence of my teaching. And like the bulk of my teaching evaluations are coming from intermediate algebra, which is not helpful to me because like that's really not my strong suit. Like people don't want me for intermediate algebra. It's not. They don't want to be explained math. They just want to be told, do this, which is not really how I function. But anyway, for the final, the other thing that was on my mind, and I will write an announcement that has a little bit more pointers, but once I write the final, but the one thing that just popped off that occurred to me is you guys were kind of struggling on the identity problems. It would be a good thing for you to like try to work the problems in the simplification section in the book on like simplifying trig identities, because I asked some pretty simple ones of those that just kind of floored you guys, and that there will be something like that on the final in terms of like just show you an example, something like simplify tangent over sine x, like simplify that. It could be something as simple as that, and how would you do that, right? Well, this one, tangent's what? It's sine over cosine, right? So you've got, so you got that. You could leave that as the answer. Of course, you could also write the answer as secant x, right? So the simplification problem can be something as simple as that. I might ask one like that, and I might also ask one that actually requires multiple steps and using like sine squared plus cosine is 1. Like we did work some, it took me about 5 minutes of step, 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 only to get this like complicated thing works out to just be 1, you know? So there are more interesting ones like that. But I also learn a lot about you guys just by asking a simple one like this, because students who are passing this class should be able to do this one, right? And if a student can't do that, that doesn't mean that they're necessarily failing the class. It just, if they can't do this and 10 other easy problems, then, you know. But no, I forget, when is the final? Tuesday.
I think it's 2 to 4.
Okay, so you guys know, that's good. I'm going by the official final exam time, which I have looked up multiple times, and I continue to forget and have forgotten to write down for you guys. But anyway, so that's that. Just when you're done, give them to Augustine over here. She'll take them to the secretary for you guys.